Computer measurement systems are no longer the exclusive turf of the electrical engineer. Scientists and engineers of all types now extract real-world data from physical systems and use it with computers for analysis and automatic report generation. The system starts with some type of physical representation of data. It could be pressure, it could be turbidity, oxygen demand, but this physical system is then fed into some type of transducer or sensor, which then converts that physical phenomena into an electrical current or electrical voltage. That then gets possible signal conditioning. Signal conditioning might be an averaging function. It might be a low pass or high pass where unwanted frequencies are discarded. Could be several things. Once the signal is conditioned, it can then go into an analog to digital converter, sometimes called an A to D converter, which converts the analog or continuously variable current or voltage into a series of ones and zeros for manipulation by the computer. The computer measurement systems are also known as data acquisition systems. They can also be used in large applications to then, with computer help, start controlling large plants and things like that. We will just concentrate on the idea of a data acquisition system. Now, data acquisition systems or computer measurement systems can go from the extremely inexpensive system which can read ones or zeros on, off, open or closed, a very simple type of measurements, that can be fed directly into, let's say, the USB port of a computer, or they can be very complex systems, much more expensive, of course, which can, let's say, in this case, monitor an internal combustion engine with such things as incoming temperatures, pressures from the turbocharger, to even pressures inside the combustion chamber, exhaust gas temperatures, coolant temperatures, and things like that. So the application can be from very simple and inexpensive to extremely elaborate. They can be portable, or they can be fixed systems, let's say, in a laboratory environment. Data acquisition systems, be they simple or be they complex, can be connected to the computers in any number of ways. It might be as simple as a USB cable, it could be wireless internet, it could be hardwired internet, or possibly some type of proprietary cabling system, for example, in large plants. In all cases, though, when setting up some type of instrumentation system or measurement system, several questions have to be answered or at least considered. The first one is, when you look at the physical parameter that you are trying to measure, temperature, frequency, pH, is there an appropriate sensor which will measure that physical parameter and then convert it to a voltage, a current, maybe a variable pulse stream or something like that? And then the question is, what does the computer input look like? Is it compatible with the output of the sensor? And what is the range of the sensor output? For example, if a sensor can go from 0 to 10 volts, but yet the computer's input range is 0 to 5 volts, something needs to be done to make them compatible. Additionally, there's the question of error. How accurate do you need the information? Is your sensor accurate enough? Also, there's a question of long-term accuracy of the sensor. Does this sensor degrade with time, or is it fairly constant? Things like that. Also are sources of noise. Many times with cabling or even with wireless, you can end up with sources of noise. It could be everything from a nearby lightning strike, radio transmitters, be they cell phones or be they CB radios. It could be power supply fluctuations brought on by the starting or stopping of large motors. So these things need to be addressed. And many times, some noises can be filtered out, they can be averaged out, and other times the computer might say, if this particular input is outside of this range, it's a piece of noise, we'll throw it away. Finally, there's a question of accuracy. How much resolution do we need in our measurement? And that will determine the number of bits of information that the computer will take in. In other words, the word size, or how many bits per representation of the physical parameter being measured. And another one is the sample rate, or how fast the signal is changing. There is the possibility that you can undersample a signal, which means what appears to be a low frequency was actually a high frequency in your measurement. This can be important in many cases. So let's give an example of a simple case where we have a structure. It could be a bridge, it could be a machine, maybe some actuating arm of a robot or something like that, where we just want to measure the linear distance between 2 points. We'll say that our distance to be measured goes from a negative 10 millimeters to a positive 10 millimeters, but we want to have a resolution of 0.01 or 1/100th of a millimeter. We'll say that our sensor has an output voltage between 0 and 5 volts through a resistance of 1,000 ohms. Note that we've described a Thevenin equivalent. It has a variable voltage, but it still is a voltage source in series with a resistor. We will assume that our computer is 25 meters away and that it can accept a voltage input of 0 to 10 volts into its 10,000 kilo ohm, or 10K or 10,000 ohm input. And we'll also say that due to vibration, our output can change as many as 500 times a second, or 500 hertz. And our job now is to find the sources of error, propose fixes, figure the number of bits needed on the computer input to get the type of accuracy we need. So the first step is to draw a picture, at least initial picture, of what this first pass version looks like. So here we have a first pass diagram of what our system looks like. We have our sensor, which is the 0 to 5 volts, depending upon the input distance that we measure from our physical system. We also said that we have a 1K resistor in it in series. So here's our Thevenin equivalent drawn in a dashed box for our sensor. We have a cable of 25 meters that goes to a computer, and notice that the computer can simply be modeled as, in this case, a 10K or 10,000 ohm resistor. What we have here, when we take a look at it, is a voltage divider, which means that not all the voltage from our sensor is going to make it to the computer. We are going to have a voltage drop across the 1K resistor, and using the voltage divider formula, we'll see that the Vn, the voltage seen by the computer, is going to be a little over 90% of what the actual signal was. So we can handle this in a couple ways. One way is, if we're doing a simple one-off and we're not mass producing this, is we could build a calibration table as long as we can characterize the sensor accurately and the load that the computer presents. Other examples that we will see later will be an amplifier, which will reduce the loading. Now notice we now have a question of, we have, yes, 10, negative 10 to positive 10, or we have 20 millimeters worth of distance that we have to measure. But we want to have a resolution of 0.01 millimeters. So what that means is, conceptually, we take that 20 millimeters worth of distance that we want to measure and we chop it up to pieces of 0.01 millimeters apiece. When we do the math, it means we have 2,000 possible values. So what this means is the system in our computer has to be able to represent one part in 2,000. A binary bit is either an on or an off, a 1 or a 0, and the number of binary bits necessary is going to be 2 to the n, where 2 is either an on or off state, and n is the number of binary bits. So 2 to the n has to be equal to or greater than 2,000. With a little bit of math, we find that we're going to need at least 11 bits. Any doubt, you always round up. Like if we got 10.9 bits, we'd say, okay, that's 11. If you have more, that is no harm done. If you have less, it just means that you do not have the resolution you need. Looking at it another way is, if we took this 0 to 5 volts and divided it into 2,000 parts, it means that we have to have 2.5 millivolts of resolution in order to get that accuracy. This 2.5 millivolts has to be protected fairly carefully as it makes its trip from the sensor to the computer. Everything from radio stations, cell phones, power lines, everything can add their own signal into our signal. These undesired signals are called noise. We need to deal with noise. So here we've modified our original diagram a little bit. Because the computer can accept 0 to 10 volts and we are providing 0 to 5 volts, we are not using the full resolution of the computer. That means we either need to have 12 bits in order to get our required accuracy, or we could add a small amplifier with a gain of 2 so that our 0 to 5 volt signal now becomes a 0 to 10 volt signal and more closely matches the input of the computer. Another thing about amplifiers, shown here as that little triangle, is that they can have a very high input impedance, a very low output impedance, so they can reduce the loading problem. And so now, depending upon the amplifier, we might find that our amplification is no longer with that 90%, but now a 0.99%, or very close to the actual value coming out of the sensor. Additionally, the type of cabling can be important. For example, in this case, we have what we call a shielded twisted pair cable, and this cable can be more immune to such things as radio interference or static discharges and things like that, and might act to reduce the errors that we face. The other thing that we're going to see here before long is going to be a question of sampling. If we have an input signal, for example, that changes at 500 hertz, we need to have a sampling rate that is at least twice that, or 1000 hertz. Even better would be a sampling rate of 5000 hertz. If we undersample, or if we sample at less than at least twice the rate of our signal, we're going to have a problem that will end up with a problem called aliasing. Aliasing is where a high-frequency signal, as shown here in purple, is undersampled and it appears as a low-frequency signal. This can mean that what you thought was a low-frequency signal is actually a high-frequency signal, and if the frequency of your measurement is important, you can end up with errors. So the idea of having a high-frequency signal shown as a low-frequency signal when you actually do the measurement is an error that you will need to deal with. A couple ways to deal with this. If high-frequency signals are not important to your measurement, you can filter them out. Another approach is you have a higher sampling rate so that you are able to adequately capture the high-frequency signal. Finally, we see that in this overall problem, there is not a specific one-size-fit-all answer, but the answers are going to be a function of the system you're trying to measure, the frequencies you're trying to measure, possible noise sources, what your sensor looks like, what your computer looks like, and the overall resolution. So this is not a nice problem that has one answer for all cases. It's one where it has to be investigated.